Okay, so last time we already introduced a different method called steepest descent. So it's the unconstrained optimization method based on gradient analysis without calculation of Hessian. So we only need first order derivative. We don't need second order derivative. However, when we use steepest descent, we tend to move like a zigzag, following some kind of zigzag trajectory. So if I make a drawing, if this is the contour of your objective function, and this direction being the direction for function value decreasing, so we call the descent direction, right? And this is your objective function contour. And if you are having a initial gas somewhere, so for Newton's method, think about the Newton's method. If this is xk, and let's think about Newton's method. Right, this is Newton's method. And let's also remind ourselves about the steepest descent. Steepest descent, right? Steepest descent looks like this. So the only difference is that in front of the negative gradient in the Newton's method's equation, there is an inverse Hessian. And in front of steepest descent, there's only a scalar. Okay, and the scalar is an unknown scalar. You don't know the size of it. You need a sub-problem, a secondary iteration, additional iteration, to find out what is the step size, how far you go along this direction. So if you make a drawing of the negative gradient direction, this is the negative gradient direction, right? So it doesn't point to the optimal solution. The direction doesn't pass through the optimal, unless you are very lucky. And the goal for alpha is to find out step size. How far away should I move so I can find the lowest point along this particular direction? Okay? And so what happened to Newton's method? Hessian matrix is a square matrix. After inverse, it is still a square matrix. So when you have a square matrix multiplying a vector, it's a kind of transformation. So it transforms the direction of negative gradient and also change the length of the vector. That's what transformation matrix does. Transform uh, the direction and the length of a vector if you pre-multiply a vector, right? So Hessian inverse actually help you to make the proper turn on the direction and also tell you what's the proper step size. So right here, it's because of the transformation based on Hessian inverse. It tells you where is the good direction and how far you should move. So in Newton's method, we didn't use the step size. We didn't figure out the step size. We didn't need to. Okay? So Newton's method is great, but it's costly. The drawback of Newton's method, costly. So Hessian calculation is costly. Okay? And the drawback of steepest descent. The drawback of steepest descent may not be effective. The steepest descent tend to move along this zigzag direction. So it doesn't point to the right direction all the time. So it's making this 90-degree turn all the time. Okay? So do you know why the steepest descent always make 90-degree turn? Let me explain to you why. So if you take a look at the contour, if I make another drawing, I will try to make it more dramatic. Kind of like a more nonlinear shape. Okay. So let's say I have some kind of function that is having the contour like this. And maybe the optimal is somewhere there at the left lower corner. And if I'm having like a cave design point right here. So as I mentioned earlier, if you try to determine the direction of the gradient, it's perpendicular to the contour. So if you try to draw the contour of that pass through the cave point, it may look like this, right? So the gradient direction is gonna be perpendicular. So this is the perpendicular direction. Going up is the direction for function value increasing. So this is gradient direction. And the other side is negative gradient, right? Because going down, function value drops. Now, if I use steepest descent, I will be moving along this particular direction, and I will try to find the position with the lowest function value, right? So by visualizing, trying to observe the trend of the function value, I can tell the lowest point probably is here. Probably here. So this is your xk plus 1. So why is it there? Because if you try to draw the contour that is tangent to this red line, it's gonna be like this. Okay? So when you try to find the position with the lowest function value, that means you're trying to find a point on this straight line. And if you pick up another point right here and try to draw the contour of the function value, you will realize it's having a higher level than this particular one. This particular one, the tangent contour, should have the lowest function value. Okay? And then from xk plus 1, if you do the gradient analysis, you will then realize the gradient direction is always perpendicular to the function contour. So it's gonna be this direction. This is negative gradient. And it's gonna be 90 degree right here. Because gradient vector is perpendicular to function contour, right? And by steepest descent with optimal step size, you find the point that is the tangent point at the line search and contour of possible lowest level, right? If I explain in this way, this point is the point along this line search, and it's gonna be the tangent point. Tangent between this straight line and the most possible contour that has the lowest function value, right? And when you do gradient, the gradient is going to be perpendicular to the contour. And since this is the tangent point, so this negative gradient is also perpendicular to the previous negative gradient. So this one and this one, they are perpendicular to each other. That's why in steepest descent, you are always doing this kind of 90-degree turn, zigzag. Okay? And that makes it ineffective. It's not a very efficient way to find your solution. It's like you are you guys are from Paraguay. There is no snow over there, right? It's very super hot. Have you tried skiing? No. So you obviously you have seen movies, videos about people doing skiing, right? So if you try to ski, what happens is there's a snow mountain, and usually you travel to the bottom. There is like a house, like a building for you to put on your equipment, and then they have this kind of how do you call that? Like a device sends you to the top. So it sends you to the top to the mountain. So the contour is like a snow mountain, and then the goal of the person who ski is to ski back to the house, right? So I always use this skiing as the story of the iteration process of optimization. So the most effective way to ski is to do what? To ski toward the goal. But imagine in that day, there is a huge fog. You don't know which direction is the house. So you are like X point. You are like trying to find out, okay, should I go this way or go that way? Okay? And then what is steepest descent? It's like, okay, if I go here, it seems like I could be dropping faster. Okay, I go here. So that's steepest descent. But imagine you are the person who skis and then in the snow mountain, every time you figure out, oh, this is the wrong direction, I will make a 90-degree turn. That's a very stupid way to find the goal, right? You always turn 90 degrees. That's why steepest descent is not very effective. It's always doing this zigzag. And today, I'm going to introduce a different method called conjugate gradient. So the idea of conjugate gradient is that can we make adjustment of this searching direction with some knowledge during the iteration process? So is it possible that I already kind of know the shape of the snow mountain, the contour? Can I not turn 90 degrees? Can I just make a smarter turn, move toward a better direction? If I'm right, probably I can move toward the goal in a closer direction. Then I may not need to do this kind of zigzag too many times. Okay, so that's today's what we are trying to do in today's method. Okay, so the method I'm introducing is called conjugate gradient method. Okay, so what does conjugate direction mean? So there's a let me define. Let us define this word conjugate. So the idea is that for two vectors to be perpendicular to each other, if there are two random vectors, so you can say given two random but different vectors, and also may not be perpendicular to each other. So they are just two random vectors, and I'll give them names, D1 and D2. Okay? So what is a way to make them perpendicular? Maybe I can transform one of the vector, let's say D2, change its direction and change its length maybe, but the most importantly it's the direction. So if I can change one of the vector's direction, move it to certain new direction, then D1 and D2 can be perpendicular to each other. So here are like some definition terms. So we can define a symmetric. It has to be symmetric. Matrix. Let's call it Q for now. And D1 and D2 are said to be, here are a very important term, Q orthogonal. There's a term called Q orthogonal. Or conjugated with respect to Q. So there are two different ways to describe this special transformation and relationship. If something happened, if what? Q1 dot D1 dot Q dot D2 equals to 0. Or write it down in the way you like it without using the dot product, using matrix multiplication. So D1 transpose Q matrix D2 equals to 0. So the idea is that if you transform D2 towards certain new direction, and if Q is properly chosen, and then after the transformation, D1 dot the resultant direction of QD2 equals to 0, that means after the Q transformation, D1 and the new D2 are perpendicular to each other. So we call this Q orthogonal. Okay? Or you can say conjugate with respect to Q. So why do we do that? Why do we introduce this kind of so-called conjugate gradient? So originally, when we handle gradient-based approach, if when we are at xk plus 1, if we can figure out a way to apply some kind of transformation on top of this negative gradient, and after the transformation, it becomes more like a nice circular way. So right now it's very nonlinear. So it's when if you have Newton's method, when you have or if I say if the contour looks like this, like an ellipse, then when you try to figure out the gradient direction, negative gradient direction, it's going this way, right? But if I can transform this elliptical shape into a circular shape, then when I evaluate the gradient, it's actually moving toward the center. So it's like, is it possible to do this kind of transformation? So after that, when I implement this kind of gradient search, it's pointing toward a better direction. That's why some kind of transformation is involved in conjugate gradient approach. Okay, but how do we find this kind of transformation? So still we have to derive this algorithm starting from the very fundamental. You cannot just make a guess. So like earlier when we introduced Newton's method, we introduced second order Taylor expansion. From there we start to derive some mathematical equations. So today I'm going to do the same thing. Okay? So first of all, we need, again, second order Taylor expansion. At expansion point xk. So I will write it like xk without, do I use the lower bracket? Lower k, yeah, that's lowercase. In my notes, in this particular note is a lower k. So I'm going to use lowercase k. So k represents kth iteration, okay? And I am not writing down the bracket. So it's a more effective way to write, okay? So let's do Taylor expansion. So a function f is similar to fk plus x minus xk dot product gradient fk plus 1/2 of x minus xk dot product Hessian k dot product x minus xk. So from here you can already see I'm trying to make the notation simpler. Yeah, so you don't need to write a very long version. So gradient fk means you evaluate the gradient vector and then plug in the xk. Hessian k means is a Hessian matrix with all the second order derivatives, and then you plug in xk. So if I write it down, what it look like. So it's gonna be maybe I is fine. It's a vector of all the first order partial derivatives, and then you plug in xk. Okay, and then what is Hessian? Hessian basically is all the second order derivative terms, and after you perform second order partial derivatives, plug in xk. So if you forget what that is, okay? So this is a second order Taylor expansion at xk. So I will now give some numbers to various equations. So later on I can recall certain equation numbers. So this is my equation 0. So this is equation 0. Okay? EQ means equation. Okay. Now, what I'm going to do next is to take the gradient of this particular equation. So it's like take the gradient operation, or I can say, so basically it's like take a first order partial derivatives, basically gradient. If you do that, you will have gradient f equals to, okay, when you take first order derivatives, all the constant terms disappear, right? What are the constant terms? This is a constant term, and this one is a constant term, and inside the Hessian you will have a constant term. So anyway, I just write down the result. Right here, this one multiply this one. This is like a constant times a variable x. So if you take partial derivative, the x disappear. It's like a 2x, take 2x prime equals to 2, right? So what's left is just the coefficient. So right here, this is what's left is right here. Okay? Now, on the right hand side, you can take derivative with respect to the first term, then the right hand side is the remaining term, and also 1/2, plus you take derivative with respect to the right one, then whatever in the front is the remaining term, and also with 1/2 right here. So both terms are the same. So at the end, it's like this: 1/2 of plus 1/2 of the front. And last time we already talk about they are actually the same term because Hessian is symmetric. So at the end is this. Because both term has a coefficient of 1/2, right? This is the end. After you take the gradient operation. So I'm gonna call this equation number 1. Okay. So there was equation 0. This is equation number 1. Now let's think about what's the common term for gradient approach or linear approach. We always try to move in this way. So we're going to define an equation like this. xk plus 1 equals to xk plus alpha k times dk. So here we introduce a new vector called d. So d is like a directional vector. Okay? So it's a new vector. And because we are trying to find a new direction, so instead of using negative gradient here, we just replace it by a vector with a new symbol, d. So it's our moving direction. So this is the step size. And it's a scalar. And this is the moving direction. Okay? So later on, we are trying to figure out how does D look like and how do we figure out alpha. Okay, so right here, there are more new definitions. And if we are actually using steepest descent, in this case, dk is negative gradient k, right? This is what we already know. But for conjugate gradient, we are going to introduce something new. So this is newly introduced. Also negative gradient k, but with some additional terms. Right here, the new terms are plus beta k minus 1 and d k minus 1. So what is that? So learning from steepest descent, we still think negative gradient direction is a pretty good direction. However, can we make some adjustment? But in conjugate gradient, when we try to make this adjustment, we just introduce new terms and allowing this new term to move, to change the angle of negative gradient. So it could be like in this drawing. It's like you were supposed to move along this way by steepest descent, but that particular new vector could be going a little bit toward up or it could be a little bit toward down. Then your new direction could be changing, right? So we introduce new information to the conjugate gradient equation. And right here, this is basically the previous moving direction. Okay? And what's beta? It's an unknown parameter, another scalar. Okay? So it's like, can we use what we have, how we moved in the previous step, use it in my current step? So it's like a memory, short memory. It's not like a long-term memory, it's a short-term memory. So it's similar to, it's an idea of short-term memory. So maybe in your project, can you introduce more terms that try to use all the previous moving directions as a reference? So maybe I can choose the current direction even more properly. Then it's like an idea of including short-term memory and long-term memory. Or maybe can I introduce even more terms by with moving directions when I solve different problems? Then it's like memories of the past, right? But that's for just an idea for you, right? Right now, for conjugate gradient, it only cares about the moving direction, one iteration in the back, right? One iteration early.
Excuse me. This is interesting. If we extend this idea, does it look like a PID controller?
Maybe you can do PID here.
PID?
Maybe. Yeah.
Interesting.
It's like looking for the goal. Yeah. The PID idea has the gradient,
Yeah.
but PID also has the integral. So far, we didn't do anything about integral. Yeah, that's a good idea. I didn't know if there is a PID gradient-based solver. Maybe there is. I don't know, because there are like thousands of algorithms being developed. I don't know all of them, but yeah, it's kind of like that. Okay, so this is like a PD solver, only derivative. Right? If you think of this algorithm in that way, kind of like PD solver. Okay, let's continue. So what's happening is now you introduce another unknown, beta. You didn't tell me what is beta. So without knowing beta, so far it's still not very helpful. Before we move on, I'm going to call this equation number 3 because we need it later on. Okay? Now, here comes the Q orthogonal. So we want to, since there are dk and dk minus 1. So there is a direction that I want to move right now, and there is a previous moving direction. So these two vectors, can I introduce conjugate direction? The concept of conjugate direction here. So we want to make these two vectors some kind of Q orthogonal. So that's the goal is to try to achieve, but this time not Q orthogonal. Let's try HK orthogonal. Between dk and dk minus 1. So we want to play with math. So right now there is an unknown beta. Can we figure out how the beta should look like? So dk and dk minus 1 becomes HK orthogonal. Okay? So when we try to achieve that, something must satisfy. By definition, dk and dk dot hk dot dk minus 1 must be 0. So that's our goal. We want to achieve that. So we can call dk and dk minus 1 being hk orthogonal. Okay? So this is my equation 4. And since this is going to be valid for all the iteration index k, so this is automatically valid. The dk dot h k dot dk plus 1 equals to 0. So let's call this 4 prime, additional equation right there. Okay? So it's like it's gonna be valid for all the any iteration number k. We want this to happen. Okay? So if you are okay with that, so now is the goal. The goal is to find out where is beta. So eventually, this is happening. Okay? So now we are going to recall some equation. We are going to recall equation 0. So let me copy this. Copy, paste. Okay, I'm gonna recall equation 0. Okay, but when I recall it, I'm gonna plug in one of the so instead besides recalling equation 0, I'm gonna also plug in x equals to x k plus 1. Okay, so if I do that, this is becoming, wherever you see x, there is a xk plus 1 there. So it's a little crowded. Let's move it in this way. Okay. Like this. And on the left hand side, it's becoming fk plus 1. Right? Because I plug in x equals to k plus 1. So I end up with something like this. And because of equation 2 right here, this one, let me copy. Since in equation 2, where you have this, xk plus 1 equals to xk plus alpha dk. You can actually replace here, change this to minus and change this to equal, right? So xk plus 1 minus xk equals to alpha k dk. So in the equation of 0, there's a lot of xk plus 1 minus xk. They can be replaced by alpha k dk. So now this new equation becomes, copy, paste. So you end up with a new equation like this. But inside these being replaced. Okay, so how do we replace it? By this alpha k dk. Okay, alpha k dk. Another alpha k dk, so the alpha is a scalar, so it could be moved to the front. So it's an alpha square and dot dk here. Right? And in Newton's method, we always want the second order Taylor expansion to be we always want to perform first order derivative of a function and make it equals to 0, because that's where we have the extreme point. So we are recalling that concept from Newton's method. So from Newton's method, we want first order derivative of a function equals to 0, because this is the location of an extreme point, right? And the solution is right at the extreme point. So we will do the same thing on this particular new equation that we just derived. And we are going to, but this gradient has to be partial derivative with respect to all variables. So this has to be partial derivatives with respect to all variables. Okay? So in this particular new equation, there's something that we don't know what it is yet, which is alpha. Because right here, fk is known. If you know xk, you plug in your function, you know your fk. You know the gradient fk. You know your Hessian k. They are terms that could be evaluated. But what's unknown? The unknown terms come from here. Here are this is a design variable. So this includes some of the unknown information. And right now, alpha is unknown. It's a part of the variables. So if we want gradient f equals to 0, then we also need we want this as well. The particular equation that we just derived, and we take first order partial derivative with respect to alpha k. We want this to be 0 as well. So this become valid. All the partial derivative terms with respect to all the variables should be 0. Okay? So how does it look like when we do this? What you will get is this term right here, right? And also you will have this term and the coefficient. And of course you have a square right there. So be aware of these. So when you do the partial derivative, what you get at the end is dk dot gradient fk plus, so the power of 2 comes down, so then the coefficient become 1. So there is a alpha k dk dot hk dot dk. Okay? And this equation, you want it to be 0. So right here, you can rewrite this equation in the following term. You can take out the dk, the pre-multiplier of dk, and then you can collect all the terms on the right. It's a alpha, gradient fk plus alpha k times hk dot dk, right? You can just collect the pre-multiplier. And this has to be 0. Okay? And what is that? That is we need to derive. Okay, so now we are going to do something with whatever that's inside this bracket. Okay? So we are interested in this. From equation 1 and 2, what is equation 1 and 2? So here is equation 1. Oh, equation 1 and 2, let's just copy them, paste them here, and kind of make some adjustments and move like this. So from 1 and 2, okay? From 1 and 2, we have these. We can put things together in such a way. Gradient f gradient f k plus 1 equals to gradient f k plus Hessian k times xk plus 1 minus xk. So all I'm doing right here is just plugging in xk to equation 1. And then right here, I can replace what? Right here, this part can be rewritten as some terms on the right hand side of equation 2. So I can rewrite this as dot product with dk, right? And with a pre-multiplier. Pre-multiplier of alpha k. Right? Because here, this minus this equals to alpha dk. So this replaced by alpha dk. So alpha here is a scalar and dk. So alpha times hk dot dk. So that's what you are having here. And it is telling you, pay attention to here, this equation is exactly this equation. They're the same, right? They're the same. So we just proved, if you put this back here, you just end up with dk dot gradient f k plus 1 equals to 0. That's a new equation. So we are going to call this one equation 5 and call this one equation 6. Okay. They are quite important for later derivation. Up to here, what happened? The goal, again, let me remind you, we want this current moving direction dk and previous moving direction dk minus 1 to be hk orthogonal, but we don't know how to start. So we start from the fundamental, which is second order Taylor expansion, and then we basically use whatever we had earlier in equation 1, 2, 3, keep on plugging in and try to rearrange the equation we have. And we introduce the idea of first order derivative must equals to 0. So that's where we can find the solution. Then we found new terms, equation 5 and 6, new relations. And they will be used later on. Now, again, we actually didn't use equation 3. We used equation 1 and 2, but we didn't touch equation 3, which is the equation with unknown parameter beta in the new definition of conjugate gradient. So now we are going to, we have good preparation. We are now going to do something with the beta. So now let's take a look at equation 3. So over here, equation 3 is right here. Okay, so what can we do with equation 3? So this is equation 3. This is valid for all the index k. So actually, we can have a equation 3 prime, which is dk plus 1. So index plus advanced by 1. So everything plus 1. This must be valid because this equation is supposed to be valid when we for all the index. Okay. Now we have this particular equation. We're going to post multiply. Post multiply Hessian k dk. Okay, let's do that and let's see what's gonna happen. So what does post multiply mean? That means we're going to do this. Okay, and then just do it on the equation of 3 prime. So it's gonna be something like this. Post multiply okay, let's just do this. And from the definition of H orthogonal, this is 0 because H orthogonal. This is what we want at the beginning. We want dk and dk plus 1 to be H orthogonal, and by definition, this dk dot hk dot dk plus 1 should be 0. Okay? And we had that earlier. We had this 4 prime there. Okay, so it's nothing new. Okay, now we are going to, from this equation, there's something pretty exciting. What is it? We finally can determine the value of beta k. So what is it? Beta k equals to gradient f k plus 1 dot Hessian k dot dk over dk dot Hessian k dot dk. Right? How can we do division? Because vector dot matrix dot vector is a scalar. This is a scalar. So vector dot matrix dot vector is a scalar. So scalar can be divided by another scalar. So this is the first time that you realize, oh, beta k is not unknown anymore. It's something that you can determine. So what are these terms? If you have a current moving direction dk at this k iteration, if you compute for Hessian, And also in the next step, if you perform gradient evaluation, then that's your beta fit. But still, it's very troublesome. You need Hessian, right? And you even need the gradient at the next move. So even though there's a form right here, but it's not very friendly for us. And we still need to compute for Hessian for the upper term and the lower term. So we're going to do something with it. We're going to take the upper part and the lower part separately, try to rewrite them in a newer form, and see if we can find better mathematical formats, which is easier for us to handle. Okay. Before we do that, I'm going to call this equation, it is supposed to be 7, right? Yes. Should be 7, but the way I taught this lecture in the past, I don't know, I made it 9, I'm sorry. If I change the number, then it's not consistent with my notes, then it's troublesome. Okay, anyway, let me call it 9, it doesn't matter. I'm not following the right order. Okay, so like I said earlier, we're going to handle the upper part and the lower part of equation 9 separately. So let's take a look at the upper part. Right? I took the upper part. So right here, what can we do? We can recall equation 2. So equation 2 was here. So since equation 2 said this is how it looked like, then dk actually can be rewritten as xk plus 1 minus xk over alpha k. Alpha is a scalar. It can be, a vector can be divided by a scalar. That's fine. So we're going to use it to rewrite the upper part of 9. So right here, this is becoming alpha k, 1 over alpha k, and then fk plus 1 dot hk dot xk plus 1 minus sk. Okay? And then, what else? Over here, this guy can be rewritten as something else. What is it? From equation 1. Equation 1 right here. Oops. Copy. And let me paste it here. So this is from equation 1. Did you notice that if I recall equation 1 and then plug in xk plus 1, equation 1 with x equals to xk plus 1, I end up with this, and then right here, this term is this term, right? Exactly the same one. So now the upper part of 9 can be rewritten as alpha k gradient f k plus 1 dot gradient f k plus 1 minus gradient f k. Right? It becomes something like this. That's called, or that's expand. I'm out of the, so that's at the end, that upper part of 9 becomes 1 over alpha k gradient f k plus 1 dot gradient f k plus 1 minus gradient f k plus 1 dot gradient f k. Okay, if I expand, open up all the terms, and let's call this equation 7. Okay. Right here, we are going to handle equation 7. Inside equation 7, there are 2 terms. We're going to handle the second term. So, second term here. This guy. If we try to handle the second term, we notice that gradient fk can be rewritten as something else by equation 3. So let's recall equation 3 from here. Okay. Copy it and paste it here. So this is what we had from equation 3. Okay, and right here, this particular part is the same as this particular part. So we can rewrite as using negative dk plus beta k minus 1 dk minus 1. Okay, we can rewrite in this way, and then we open up the terms. So we end up with negative gradient f k plus 1 dot dk plus beta k minus 1 gradient f k plus 1 dot dk minus 1. Okay? Once we have that, this because of 5 was here. Copy it. Because of 5. This guy equals to 0 because of 5, right? A dot B equals to B dot A, the same thing. The dot product between 2 vectors can be swapped. Okay? So that one is becoming 0. So that is, do we do something further? Let me see. Okay, we can call this one, do we? Let's call this equation 8 in case we need it later on. Okay? So what do we do now? We are going to do something further. for this particular part because we still have beta, some non-zero terms for this inside this term. It has been rewritten as these two terms, and this one equals to 0. So this can be replaced by this. Okay? And over here, we are going to recall equation 6. So let's pick up equation 6 right here. This one. Copy, paste, get rid of these. Okay, so this is equation 6. Okay, from equation 6, we now will rewrite the gradient k plus 1 by what we got from equation 6. So let's do that. So over here, this is becoming so gradient f k plus 1 dot gradient f k now becomes beta k minus 1, and what we have from the equation 6, gradient f k plus alpha k Asian k dot dk, and this whole thing dot product with okay, and this part dot product with that actually will end up with dk dot or you can, yeah, it's the same thing, dk dot hk because of symmetry dot dk minus 1. That is 0 because dk and dk minus 1 is h orthogonal. Okay, and what's remaining is this term and this term. So let's write down what's remaining. Beta k minus 1 gradient f k dot d k minus 1. So what can we do to rewrite it? We use equation 5 again. Equation 5 here. So from here, in equation 5, it tells us dk dot gradient f k plus 1 equals to 0. And this is it has to be valid for all k. So if we minus the index by 1, then dk minus 1 dot gradient f k equals to 0. That's exactly what you are having here. So this whole thing is 0. So with all that, the goal is to make this thing disappear. It took us so many derivations and we finally realized that is 0. So that was the upper part of the beta definition. we finally figured out how to mathematically describe beta, which was originally an unknown parameter. So we handled the first part first. We handled the upper part first. And in the upper part, what we did was this was the upper part. We rewrite it in a certain way with the information of equation 2, and also this being rewritten as this because of equation number 1, and over here by the and also equation 3, and by the definition of equation 5, some part disappear equals to 0, so this is a remainder. And that remaining part can be derived further. Down here, we notice that it can be rewritten as this form using the information of 6. So it's a 2 terms summing up. And the second term equals to 0 because of HK orthogonal. The first term equals 0 because of 5. So eventually, this very complex term is being greatly simplified as the only non-zero term right here. This is the only non-zero term. The light blue area, the whole thing at the bottom right here, becomes 0. So this is the only remaining term. So the upper part of 9 equals to this only, the first term only. Okay, so I'm going to copy. Very important conclusion or very important finding. So, from equation 7, this is what we got in 7, right? The upper part of 9 now equals to this. This is the only non-zero term. And we can now plug back to the definition of beta. So let's get this copy and paste. So if this is from 9. Okay, so now we can plug in the upper part, the newly derived upper part of 9. So this gives us, let's try to, yeah, that's fine. Okay, so you will have gradient f k plus 1 dot gradient f k plus 1 over alpha k scalar at the bottom dk dot hk dot dk. And we are going to call this equation 10. Okay, so we already resolved the unwanted Hessian at the upper part. We rewrite the upper part in such a form. We no longer need to compute for Hessian in the upper part. But for the lower part, we still need to compute for Hessian. So now we are going to handle the lower part. Okay? Here, lower part of 10 is, yeah, this whole thing. Copy and paste. Right? And we are going to rewrite it by the information of equation 6. So let's find out what does the equation 6 look like. So this is equation 6. So this was equation 6. Okay? From here, you notice that some part of equation 6 is similar to the lower part of 10. So right here and right here, right? There are some common terms. So how can we handle the lower part of 10? What we can do is from the equation 6, what we can do is we can pre-multiply, pre-multiply dk. So what you get at the end is gonna be dk dot gradient fk plus 1 equals to dk dot gradient fk plus alpha k dk dot Haitian k dot dk. So now you actually found out that this whole thing, the lower part of 10, is shown right here, exactly the same. Right? That's exactly right. So that tells us that the lower part of 10 equals to dk dot gradient of k plus 1 minus dk dot gradient fk from this information. Right? And we're going to call this equation 11. Okay? So from the equation 11, in the first term, we're going to recall equation 5 again. Equation 5, we did this earlier. Equation 5 is right here. So copy equation 5. Because of equation 5, you notice that, let me use color. Here, dk dot gradient fk plus 1 equals to 0 because of equation 5. So now lower part of 10 equals to negative dk dot gradient fk. Okay? And we are going to rewrite it. Can we directly use it? Yes, we can, but we don't want to use the information of dk in beta. Let me explain why. So right here, when we first introduce beta, right here, we want this beta can be easily computed, not requiring information of dk. Because we need this to compute for dk. If the calculation of beta requires dk, then it becomes a kind of cycle, right? Then you cannot determine what is beta k minus 1. So over here inside the derivation of beta k, here, we now figure out the bottom part can be rewritten as negative dk dot gradient fk, but we don't want dk to be shown because we compute beta for dk. Now, if inside beta there is a requirement of the value of dk, then you don't know how to evaluate beta k. So we want to rewrite this term in a newer form. Okay, so right here, we are going to recall equation 3. We're almost done. Equation 3 is right here. So earlier we know equation 3 looks like this. So we can rewrite lower part of 10 in the following form. Right? And let's expand the form. We will have gradient fk dot gradient fk minus beta k minus 1 dk minus 1 dot gradient fk. Okay, there's equation 5 coming to the play again. So right here, equation 5 is just right here, and if you minus the index by 1, you end up with dk minus 1 dot gradient f k equals to 0, right? This is exactly this term, and this equals to 0. So amazingly, this ends up with gradient fk dot gradient fk. So this is the lower part of 10. Where is 10? 10 is right here. Copy it, paste it here, and then get rid of these. Delete, and then delete, and then copy. Oops. Copy and paste. So finally, this is beta k. This is what you get, beta k. And how about beta k minus 1? Just minus all the index by 1. Okay? This can also be evaluated by the norm of the vector and square. If you, why? Because A dot A equals to its length squared, right? Because of that. If you do not like to perform dot product, you can, it's the same math. You can evaluate the length of the vector and then take a square. The same thing. Okay, now we know beta kn minus 1. So back to the very beginning. What happened? We tried to find out, is there a way that we can define so-called the conjugate gradient so that dk and dk minus 1 could be hk orthogonal? And we have this newly introduced term with a scalar multiplier, beta k minus 1, which is something we didn't know, multiplying the previous moving direction, which we should know, because we moved from the past. We should know what was the moving direction, but we don't know what is this multiplier. So with all those derivations, we figure out, oh, beta minus 1 can be evaluated. So the conjugate gradient equation will be written as this. That's the conjugate gradient equation. So if you want to move along this new direction, you can move along the negative gradient plus this multiplier times the previous moving direction. Okay? So now I will tell you what's the solution process of conjugate gradient. Finally, solution process. Okay, so at least you cannot memorize the derivation. So did I. I cannot memorize it. I need to rely on my notes. Too many plug-in from equation 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. But now you know the final form. All you need to do is to know how you can use it. But the way mathematicians derived this equation is very beautiful, I think. So if in your project you would like to introduce new equations, maybe that would be a good reference for you. Good reference about how mathematicians rewrite certain terms into a newer form and try to replace unwanted calculation by something simpler. Okay, so solution process. You have initial guess, so starting from k equals to 0, and you have an initial guess, right? Then all you need to compute would be your kth gradient. But what's interesting right here is that right here, your xk plus 1 equals to xk plus alpha k gradient fk, but where not gradient fk, sorry, dk, where dk equals to negative gradient fk for k equals to 0. So initially, there is no k equals to negative 1. So there is no negative 1 iteration. So initially, in the first iteration, you just perform steepest descent. So this is just like steepest descent. And right now we are introducing the solution process of conjugate gradient. Okay? But in the first iteration, your dk is just like steepest descent. Okay? And then your dk equals to negative gradient of k, and right here, plus gradient fk length square over gradient f k minus 1, the previous one, length square, times dk minus 1 for, or I can say otherwise, or just for k greater than 0. Okay? Did you notice something? We still don't know alpha k. We just figure out what's the new direction, but we still don't know the step size. So what do we do for the step size? Line search, just like steepest descent. So right here, you won't know the step size alpha. You still need to perform the subproblem. So right here, goes to the subproblem with iteration index, a new iteration index. I use m equals to 0. Initial guess, alpha m. So this is my initial guess of the step size. And right here, if I solve it by 1D Newton's method for the line search, this is subproblem of line search. Then I need f prime of m and f double prime of m. I need these two, and then alpha m plus 1 equals to alpha m minus f prime of m over f double prime of m. That's Newton's method. And then I will do convergence check. The absolute value of alpha m plus 1 minus alpha m, is it smaller than a small value? If not, then go back to here. If no, so here index number advanced by 1. Okay, if yes, right here, ish. If yes, your alpha k equals to the optimal from the subproblem, and it will be your latest one. Oops, sorry. Okay, now back to the main loop. You will do the convergence check by comparing xk plus 1 and xk and see if it's smaller than a small number. If not, then goes to here. And index number advanced by 1. If yes, x star equals to xk plus 1. Okay, so this is the final solution process of conjugate gradient method. I'll give you some time to digest. Actually, the only difference is here. If you do not use this equation when k is larger than 0, then you are just still Stevens decent. So the only difference is right at the second iteration, you start to change your searching direction by this interesting term. Like I said, the short-term memory in the previous iteration with this unique pre-multiplier to change your moving direction from negative gradient to a new direction. If you do that, starting from the second iteration, you still perform the exact same line search, you are doing conjugate gradient. Okay? Any questions?
Is there a visual for the conjugate? Can you like draw it in the...
Basically, it will. What's gonna happen is, for Stevens decent, it's gonna move along this perpendicular direction. But for conjugate gradient, it will turn toward this goal. And when you perform line search, it moves toward the goal more easily. That's the only way you can
Expand that, but
just change the direction a little bit.
how does it relate to length?
By what was derived. It was done mathematically. So take a look at what was utilized. We didn't introduce new concept. We started from second order Taylor expansion. We want the first order derivative equals to 0. And for the conjugate gradient term, we just introduce a new way to adjust this equation. So how this should look like, so at the end, it will become the idea of HK orthogonal. So the HK orthogonal is like the concept of this. So originally, in the nonlinear space, the gradient doesn't point toward the center. But in a transformed space, when you perform orthogonal direction movement, it will point to the center. So the idea is like, what is the transformation to achieve this? That's the idea of HK orthogonal. Okay. Yeah, so it's not very straightforward. And also the derivation is not very straightforward. But anyway, let's see how it looked like in MATLAB. Okay, now, finally I can sit down. Okay. So this is the code that I had earlier, and I just rename it as conjugate gradient. But nothing was changed. Now I'm going to change it. So this was my steepest descent code. I'm going to change it as conjugate gradient. Okay? And this was the code with symbolic. The other code is the one with finite difference. So I'm going to modify both codes at the same time. Okay? So inside conjugate gradient, in the first iteration, nothing is different. Everything is the same. But starting from the second iteration, I need to make a change. So I need a short-term memory of the previous gradient. So every time I complete the derivation, I need to have a short-term memory of the moving direction. So I'm gonna, okay, whenever I compute g, that's my gradient, I'm going to have like a short-term memory called previous g. So g pre is my previous g. No, I shouldn't do that. I should do this when everything is done. And when everything is done, right here. Right before I am moving to the next iteration. So whatever g I have in this particular iteration becomes my previous g, right? Okay? So I'm adding this on both codes. Okay. Now, what I'm going to do is I am going to introduce the d vector. So d, I'm gonna say if k equals to 1, then d equals to g. Oh no, negative g, right? Else, my d would be different. So d would be negative g plus the norm of the, the negative, negative g. I also need a previous d. So at the end, I also need a d pre equals to d, short-term memory. So when I'm back to the beginning of my second iteration, I already have d pre. So here I will have the norm of my current g, and then take a square, divided by the norm of my previous g, take a square, times my previous d, right? So this is exactly what conjugate want us to do, right? And here, this particular equation, I better do the substitute. I better do the substitute here. So here, I will. Do I substitute here or? Yeah, let me just substitute here. Substitute here, and then, yeah, I know the equation looks long. Yeah, okay. So I'm here, it will be plus and the d. Right? So first iteration, this is basically steepest descent. second iteration, I will have this new term. And then here, the rest will be the line search that I had earlier, last week. I think that's everything. So let's do the same thing for finite difference there. I will need the D pre, so the D pre here. And right here I need the G. So I will copy everything here. Copy all these. And yeah, substitute in this particular yeah, that's it. So in the first iteration, negative gradient, right? Second iteration, negative gradient plus all the short-term memory term and the previous D. The rest are the same. Okay. Do I need to for the finite difference? I calculated the function call. Did I introduce new function calls? No. Because these are when I use finite difference, those are the only times I perform function call. And in the line search, that's only where I perform function call. When I keep a memory of the previous G and the previous D, doesn't require any additional function calls. When I move on to the conjugate gradient equation, it doesn't require any new calculation. It just gets some information into my equation to update my moving direction. Okay, so that doesn't introduce new function calls. Now let's take a look at how the solution process look like. Something's wrong. 27. So it's the symbolic thing. FA equals to FA is XA or XA. Okay, let's take a look at how the XA look like. So XA is symbolic. I should let me take a look at XA. Oh yeah, that's fine. So how about next iteration? Okay, XA again. When I compute for D, I should make it numeric, not symbolic, because of the way I utilize the symbolic. So these are symbolic. So I should make it a double. This is substituting. So I will make this one a double. Okay. Then should be fine. Still not correct. That's not the issue. Let's take a look again. First iteration, XA is fine, okay. Second iteration, no. I know what's wrong. When I have the short memory of the previous G, I memorize the symbolic G. I should memorize the G with substitution, plugging in. So I should memorize this guy, not the symbolic G. Okay, so I should do the same on the other code as well. I think that's it. So let's see if that's resolved the issue. Yeah. Okay. Last time I was trying to display this M. I don't need this anymore. Do not display M. Okay. And then solve it. 16 iteration. Let's solve quadratic problem first. Okay, and then it doesn't look like it's working. Did I went into here? D step. Okay. D is current one over previous one, right? G previous, G previous, G pre, G. G previous 22 and 10. 22 and 10. How about D previous? Negative 22 and 10. Yep. Let me check on the equation. Did I plug in the right equation? Current over previous, yes. Should be correct. Okay. Continue. Okay, let me call the steepest descent and see the difference. This is a steepest descent. Sorry, I do not display this. And then solve a square problem. 8 iteration, conjugate gradient. 7, slightly faster. Let me make a more difficult problem. If the power, the coefficient here is 10, it will become harder to solve for steepest descent. Yeah. 7. Conjugate gradient. 6. Didn't. I feel like something is weird. XA. Something is wrong. Something must be wrong. FA. X. I didn't. Here, I didn't update the most important equation right here. It is still performing steepest descent. That's why I feel like not improved much. I should multiply D. Yes. Okay. That's how it should look like. And for here, plus D. Right? Okay. Conjugate gradient. Okay. 3. How come not a number? I need to know why it's not a number. Okay. Second iteration, third iteration, okay. XA. Yep. Here, 0 over 0. 0 over 0, so not a number. So my code didn't try to avoid 0 over 0. So right here I should say if DFA equals to 0, then basically a m plus 1 equals to a m. Else this, because my code didn't worry about 0 f double prime, but I should worry about it. So right here, numerically, if you found DFA exactly equals to 0, then f double prime will be 0 as well. Then you will have a 0 over 0. 0 over 0 is not a number in computer. So if you write it in this way, it will avoid not a number results. Okay. So I will update the bug in right here in the line search. If DFA equals to 0, then the alpha equals to the previous alpha. Otherwise, try to follow Newton's method for the line search. Yep. So that resolve the bug. Let's compare again. We can now solve the same problem. Okay, this is steepest descent. Okay, you can see how this method is trying to move along this zigzag 90-degree turn. Eventually stop right here. Totally 7 iterations. But if I use conjugate gradient, right at the second iteration, right here, it didn't zigzag anymore. It moved toward a pretty nice direction. This is a quadratic problem, so in the second iteration, so-called the HK orthogonal will transform the elliptical shape to this circular shape. So it will bump into the right direction after the transformation. That's why in the second iteration it was able to find this proper direction due to this HK orthogonal, HK transformation. So if we are solving a more difficult problem, let's say this is 4th order right here, and this is 4th order right here, Then you will see, let's see, how steepest descent struggled. Okay, this is the struggle of steepest descent right here. Very zigzagging. Okay, this is steepest descent. Very, very zigzagging. Okay, it took steepest descent to find the solution. 34 iterations. Steepest descent, doing zigzagging. And if we solve the same problem in conjugate gradient, let's see. 17 iterations. And let's take a look at zoom in and see what happened. So it doesn't follow 90-degree turns. So all the turns, they don't necessarily need to be 90 degree. But still, it's a very nonlinear equation. It's very difficult for gradient approach. Highly nonlinear. So it requires certain movement to find out. Okay? Let's take a look at Newton's method for this particular problem. If we solve the exact same problem by Newton's method, Newton's method has the information of Hessian. Conjugate gradient took 17 iterations. Let me copy the result here. This is a conjugate gradient. Let me copy the result here. Okay. This is conjugate gradient, right? And then if I solve it by steepest descent, okay, steepest descent. It's like this many iterations, okay? And then Newton's method. Newton's method, I need to copy the problem. Okay, I did. Okay, I should be able to solve it. Newton's method took 20 iterations. So compare all these. Even for Newton's method, it struggled, but more precise. Like it was able to find 0.5, 0.0015, very precise solution. But actually, all method was able to converge right at the error smaller than 10 to the power of -3. Of course, that's the convergence criteria. The number-wise, you can see you will be. It looks like Newton's method was able to find. It looks even more closer. Okay? But numerically, they are having the same level of error. And conjugate gradient even use fewer iteration numbers to find the solution. Let's take a look at the finite difference one. Because in finite difference version, we did the function call. Okay, so let's open up the finite difference one. Let's take a look at, I need to make sure I am having the same setting. So let's make sure we're solving the same problem for all codes. And then let's use the same level of delta. Maybe 10 to the power of -4. Okay. Let's solve it by Newton first. Okay. So Newton's method. This is with, oh, yeah, I should erase these. Newton's method. Here. So with final difference, this is the performance of Newton's method. Also, 20 iteration, function call 120 times. Now, let's take a look at the steepest descent. Okay. Taking a very long time. 42 iterations by steepest descent. Okay. 432 function calls. 42 iterations. So very ineffective. Okay? How about the conjugate gradient? Among all, I think it's a very good performance. Right here. 16 iteration. Actually more function calls than Newton, but 16 iteration. Okay? So still, if you, sometimes in my lab, when we solve some problem, we still solve by Newton. Because even though you need to handle Hessian and there are so many second order partial derivatives, but overall, it may not require the highest function call. But conjugate gradient is pretty good as well. So it really depends. For different problems, each method may perform differently. It's no guarantee. But here is just for you to compare the difference between them. Okay. So that's what I'm going to introduce today.
Can you add a timing profile to see the real CPU time it takes?
CPU time, sure. It's gonna be very short. So let's say Newton's method. So this is conjugate gradient. 2 seconds, but with graphics. MATLAB took some time for drawing. Okay. And let's see steepest descent. Steepest descent 3.3 seconds. Conjugate gradient 1.9 seconds. For MATLAB, the most time-consuming part is drawing. So fewer iteration requires lower computer time. So it's obvious that the required time is almost proportional to the iteration number. But I think in optimization, the most appropriate way to evaluate an algorithm is to compare required function call and required iteration number, and also solution accuracy. Okay. Does anyone has any questions? Okay, so maybe I can share with you something about your project. Let me share. Let's see. Maybe. So this was from my PhD. Now you want to think about projects, right? So this was this is something I made up. I made up a problem. I made up. This is purely made up. Okay. It's a story that we want to work on MEMS, and from the literature, it says this kind of device can be like a micro gripper when you apply current to the silicon structure, and because of the both sides of the finger are having different dimension and so different thermal expansion. So when you apply current, it's being heated, and it's gonna bend toward one direction. So we can define certain micro gripper like this, and you can actuate the left and right. So it's like actuating the right is like this, and you can open up. You can either like a close up or open up by expanding A and B separately. Yeah, that was the idea, and at the time we assume if we apply current, the deflection is gonna be 1/6 of the length. So the design variable will be the length of the A part and the B part. And because of such a simple definition, the equation could be like this. We just made up, okay, can we minimize the total width? Minimize the, I think is, why do we minimize the width? It's like here. We don't want the size of the gripper to be too wide. We don't want fat fingers. We like thinner fingers with certain constraint. The gripping width, that is this one, has to be lower than 20. Gripping gap is this one. So it doesn't collide. Has to be positive. And the open up, when you open up, it has to be 40 micron wide at least. And we set up A and B has to be within 5 to 150 micron. Okay, that's a very simple optimization. Let's see this result. So at the end, the objective function contour look like this. The dash lines, if you minimize it, the left lower corner is the optimal. But with the 3 constraints, that shows up 3 boundaries. So at the end, if I have an initial guess, if I solve this problem, if you know how to solve constraint optimization, this is the solution. So A equals to 24, B equals to 96, you end up with the optimal design. Okay? And within this region, this is the so-called a feasible space. So all the solutions inside this triangle satisfy the constraints, but at this particular corner, it has the smallest function value. So that was the solution for this particular simple linear problem. But when I was a PhD, I was working on optimization with uncertainty. So at the time, there's an idea that maybe dimension A and B would be uncertain. So if the solution right here is uncertain, then I have a great chance of violating some of the constraints. Okay? So at the time, I applied the idea of safety factor. So when you apply safety factor, your constraint become narrow. Your design region becomes smaller. So I can only find solution inside this even narrower triangle. So the optimal solution is right here. And the probability of failure is controlled. So that was my PhD. Okay? So here is just one example how you can try to find a real problem, even though you don't really make it. Maybe you just solve it by hand, or you have simulator, or if you have some experiments in your lab, how to formulate some kind of problem with objective function, constraints. You can have 2 variables, 3 variables, more, and then try to solve it. Okay, this is one particular, a very simple example. I have another example. It's a micro, like a CVD, micro fabrication problem. Let me see. Here's another example. It was a semiconductor microfabrication process called chemical vapor deposition. So what does CVD do? CVD basically is basically a chamber with heat, and you have a reactant coming into the chamber. Because of the heat, chemical reaction will happen at the bottom. So if you have silicon wafer on the right there, there will be some chemical reaction happening on your wafer, so you can grow something. So at the time where I was working on basically silicon wafer at the bottom, if I have so-called silane and hydrogen coming from the top with some heat at the bottom, this chemical reaction will happen. So it will grow silicon on top of silicon wafer. And the hydrogen will become water coming out on the right. So this could be simulated by ANSYS. With certain boundary conditions, I control the temperature at the bottom. I control the velocity of the coming silane and hydrogen. Those are the 2 design variables. And then I was working on the numerical analysis. So the string line looks like this. Color represents velocity. This is called the impinging flow. Okay? And this temperature distribution looks like this. The bottom is heated. So only the bottom area is hot enough, so silicon will be deposited at the bottom only. And the simulator shows that the silicon at the bottom will be grown in such a deposition rate. And if you try to grow silicon at the bottom, you want it to be flat, right? You don't want it to like a dome shape. Because in semiconductor, you want everything to be grown in the even speed. So the tail of this bottom silicon wafer cannot be used because it collapses. So if I can control the temperature of the furnace and control the speed, we realize this deposition profile will be changed. So some simulations show that it's possible to have pretty flat deposition production rate. So only thing is what is the optimal temperature and speed, the velocity. Okay, so I ran simulations and I formulate certain equations to define how flat the profile is. So I use some math to get the performance. So certain math equations. So at the end, this is the this should be the production rate. This is production rate. So the x and horizontal axes are temperature and the velocity, and the third axis is representing the function. So the first function I sampled was the production rate. So you can see I did simulations with different combinations of temperature and velocity. I found different deposition rate. So obviously at certain area the deposition rate is high. At certain area some combination of T and V deposition rate is low. And also the other three are, MDR is deposition rate. PWA is DWA is working area, percentage of working area. Rooming square error is like how flat the profile is. Kurtosis is another statistical factor to represent the flatness. Okay, so this is like an average flatness. This is like a local flatness. So once I have those functions, I just did optimization. This is maximizing deposition rate subject to rooming square error smaller than certain limit, local error smaller than certain limit. So this is how the objective function look like. If I want to maximize it, higher deposition rate is the best. So lower temperature, higher velocity give us the greatest deposition rate. But this is the flatness. In this area, the profile won't be flat enough. So this area is not good. And this is local flatness. In this green area, the flatness is not good. So this highlighted area, the orange and the green are the bad, the invisible area. We can only find solution in the white area. So within the white area, there are some local optimal. I use gradient-based approach, and there are some local optimal, and the last one is the best because it has the highest deposition rate. Okay, but if you introduce one more constraint, this constraint is about working area. In this purple area, in the bottom of the furnace, many area is producing non-flat deposition. So this purple area in the contour represent poor working area. So at the end, this is the optimum. So you can see how you can you can change the way you consider the problem, and the solution won't be the same. Okay, so that was another project I can share with you. You can see that the core of the problem is not optimization. Optimization is actually a tool. The main problem is something in the practice, in one of the engineering field. Okay. Let me see if I can find a different problem for you. Okay. Someone did this. It was a microchannel heat transfer system. Okay, so anyway, those are just slides. Just make it quick. Okay, it was a heat sink microfluidic system, inlet, outlet, and we're trying to design proper size for the microchannel with different design parameters. Okay, and this is a U shape. This was a straight channel, U-shaped channel. Okay, and we modeled different functions. This was thermal resistance, pressure drop, heat flow, basically power for cooling. Straight channel, U-shaped channel. The variables are basically the parameters, I think H and W, I think, H and W. So different numbers of H and W. Basically the aspect ratio of the channel. Also same H and W, but different. One kind is a straight channel, the other kind is U-shaped channel. Different numerical performances, and then we perform optimization, basically, minimizing something and find solutions. Okay, but yeah, this is a new concept. This is called multi-objective. So it's something for the future. But just for you to know, we did a heat sink problem. We studied the functions, we put them together into different equations. Okay? Just give you some inspiration about what you can do. Let me see what else. Okay. I don't have. This is one of my students. I don't have a PowerPoint. So she's from Philippines. In Philippines, they care about a kind of industry, the food industry. They use some technique called spray drying. They spray dry the powder egg with tapioca starch to create. So they at the end they want to get powder egg. Okay, so for the production of powder egg, they spray on like a spray in like a chamber and cooking the egg to have powder egg at the end. So inside this cooking process, they have certain percentage of tapioca starch. So this was her simulation, a kind of chamber for spraying the powder, spraying the egg and then cooking the egg and form powder. So she did simulations to see how the flow looked like, and that was it was only abstract, not a long article. Yeah. So at the end, she did optimization. There are like different, I think control temperature, control speed, and then you have production performance, something like that. Let me see what else I can share with you. William Roba. What is William Roba? Oh, this one. Let me see. Oh, this is actually a project that I work with another professor. He was using UAV to do inspection. It's a project about vision. So he was this is a real video about his UAV taking pictures of buildings and to form this huge map of a building. Okay, and then each part of this huge map is actually a pretty good quality, high resolution image, like maybe at the time maybe not 4K, but high resolution image. So it took hundreds of pictures and then stitched together. However, for buildings, there were issues. Sometimes we try to study the crack image. So at the time we did some optimization to figure out how to enhance the contrast, so you can see some cracks with more details. So anyway, this is before contrast enhancement. This is after. You can see there are actually some cracks. And in this over here, we also try to stitch multiple image into one big picture. So sometimes the UAV is not perpendicular to the building. So the picture you took may have a angular error. So at the time we did some optimization on mapping the picture back to straight. So without optimization, you can see how this door, the shape of the door is not straight. But with optimization to correct the angular error of the UAV, you can see the stitching result is more straight. So it's a optimization for minimizing the perspective error of the UAV, so you end up with a better result the shape of the geometry of the stitching is more precise. Okay, so you can see the earlier problem was a semiconductor problem with micro scale. Now is a centimeter scale in robots. Okay, so optimization can be applied in many different problems. So I will recommend you kind of have a sense of what optimization can do, but you just need to find out what kind of problem you're going to apply. And no matter what kind of problem you're applying, the most important thing is try to find what are the variables, try to find what are the functions you care about, and then among all these functions, what are the constraints? Constraints usually are the functions that has an upper limit or lower limit. And for the objective is usually something that you want to maximize or minimize. Okay, so I suggest you guys start to have discussions starting from this week. Talk to your teammates, make a list of the problems you would like to solve. Okay, and then if we take a look at our course schedule, today we're done with unconstrained optimization. No class next week. Due to what? Due to the holiday, is it? What happened to next week? Is it a tomb sweeping day? Is it? No, I don't. I don't remember. I don't remember why next Monday no class. Let me see. Because of the sport activity. So there's a makeup holiday next Monday. So no class next Monday. But you guys need to worry about a week later, end of March. There's an exam, midterm exam, first exam. So when you come back, 2 weeks from now, I will give you problems, and you need to solve the problem by. You need to do Newton's steepest descent and conjugate gradient in this problem, okay? So I will give you all the time, starting from 9:10 until 12:10, right? You have 3 hours. But if you know how to do it, probably you don't need the entire 3 hour. But it's okay if you want to do more. So you will have to do the exam. You have to practice. In the exam, you can bring your calculator, not your cell phone. Bring the engineering calculator or traditional calculator. Okay, but do not take out anything that has internet. Okay. I want you to memorize the equations. So I think this is a conjugate gradient, right? I guess this line is the most difficult one to memorize. So please, or do you need me to give you equation sheet? That is very easy. Okay, I will write down equations. But I will not tell you what equation represent what. I will just give you a bunch of equations. So if you have poor memory on equations, at least when you see it, you should know what is what, right? So 2 weeks from now, it's our first exam. I think this is the most important exam for the class because it's 25 points, and you have I didn't assign homework, so there's nothing forcing you to practice. Only you can force yourself to practice. Okay, and if you want to try it, I will recommend you to try these 3 methods with my codes. So you can try, just download the codes, but in the exam, I won't give you. I'm not sure what I will be giving you, but you can use my code as an example. Because if I ask you to solve with finite difference, there's a code for particular problem with finite difference. Only thing is it's done in computer, and it shows you the iteration process. And you can solve it by hand and then compare with what happened in the computer. Then you can try to figure out what happened. Okay? And nowadays, GPT is so powerful. You can even ask GPT to solve line by line. You can learn from it, right? And we did some practice in my notes. So if you still have problems, there are 2 weeks. You can send me a message. Hey, professor, I just cannot figure out what you mean in certain part. I will reply to you. But please send me message through Facebook, because I don't check my Moodle. I don't check Moodle message. You can send me email. You can send me Facebook message. I will reply to you. Okay? So I want you to do well in your first exam. So later on, you don't need to worry about dropping the course or having a low score. Okay? Any questions for today? Okay, thank you. Bye bye. That's it for today.